One of the things we talked about was the creation of your own inductors, and remember that all we talked about was taking a wire. I'm going to make sure and get my wire here again and select that, make it a little nicer, make sure it's good and seen, and all we're going to do is wrap a wire around a form, and this might be our air. Remember we talked about if we saw the dashed lines, that would be our ferrite core. If we had the straight lines, we were talking about iron core. And we're talking about the ability for this thing to keep the magnetic permittivity of keeping this magnetic field within itself, and that is just relative to the overall, right? And so what we're going to do is that we're going to look at how do we calculate that. Very simple. Just like in our capacitor, where we were concerned with the actual capacitive plates and the dielectric here. Remember we talked about this dielectric here. In an inductor, we worry about that core material and that permeability of that. And we're going to look at the absolute permittivity, and that absolute permittivity, okay, and we're going to label that as U, is going to be equal to a relative value times 1.26 e to minus 6, and that's going to be the offset of everything for permittivity. Okay, so if we know what the relative is, we will take the relative, multiply it by 1.26 times e to the minus 6, and we'll get the absolute permittivity. Alright, so if we want to know what the actual value in inductance is, we will take that relative permittivity, alright, and we're going to multiply it by the cross-sectional area, which is this right here, okay, that area, and we're going to multiply it again by the number of turns that we do on this thing. So however many times we wrap around this will matter, and then we're going to divide it by the length, how long this is. Now, as you can see, if I take the same number of windings, let's do this, 1, 2, 3, 4, 5, 6 windings, and we have, let's say, this distance of 1 inch or 2.54 centimeters, or whatever you want to call it. And if we do the same value of 1, 2, 3, 4, 5, 6, and we triple that distance, go to 3 inches, well, as you can see, that amount of inductance, okay, is going to decrease substantially. First of all, because these are not cutting into each other. They are not doing that, not working with each other to increase that inductance of stopping the AC signal, stopping the change in field. It becomes actually more and more like a wire, a strict wire. And therefore, that's why that occurs. Again, relative permittivity, let's say that if we had air, it might be a 1, and some other ones and some other values in there would increase that. That changes it. The cross-sectional area, as that gets bigger for the same number of volumes, that will also get bigger, and the number of turns increases that inductance. The thing that decreases the inductance is how long is it going to make it. You take 6 turns like this, and guess what? We will not see that same inductance, right? You can do this at in the lab. Take a piece of wire, wrap it around a pencil, and stretch it out, and keep on measuring.